This is the last of the videos on descriptive statistics. Now at this point, we've covered tables and graphs of data, measures of central tendency, measures of dispersion or variation, and our final one that we're going to cover in this video is measures of position. This is a much shorter video. Measures of position are used to describe how scores fall in relationship to another. By comparing data across groups or samples, it's important that you don't compare raw scores exactly, because raw scores come from a certain context. They're going to be tied to means and standard deviations of those samples. So we can use other types of numbers like standardized scores or percentiles as comparison points. This might sound familiar because when you took the GREs or the SATs, you also got a percentile that told you where you were in comparison to other people. So you know that maybe that year you were in the 97th percentile, or in the 94th percentile, or the 86th percentile. Now, measures of position are pretty straightforward, so I only have this one slide on it. Measures of position are all about percentiles. I'm going to enlarge this image a little bit, but they can be broken up in a little bit different ways than maybe you've seen before. Percentiles are the straightforward ones. These go from percentile 1 up to percentile 99, where you can be in the 95th percentile, the 86th percentile, the 23rd percentile, etc. But those are best used when you have very large samples. So when you're comparing students who take the GRE, where there are thousands of students every year who do that, or the SAT, where there are hundreds of thousands of high school students who take that, that's the most appropriate data set, because any one percentile has a couple hundred students in it. Whereas if I were to break those down into other numbers, it wouldn't be as useful. Now, sometimes and a lot of times we don't have access to thousands and thousands of individuals in our sample. So we break our data down in a different way. Let's skip, I'll go all the way down to this quartile area, where quartiles breaks it up into the bottom 25%, which is quartile 1, the difference between quartile 1 and quartile 2, that's going to take you from 26% up to 50. Then from quartile 2 up to quartile 3, that's going to take you from 51 up to 75, and then the quartile 4 would cover the rest of the way. Now, quartiles are most useful when you're having relatively small samples, something like the size of this class, where a single quartile in a class of 20 students is going to be about 5 students. So in that quartile, at least have a number of students. So say I'm looking at the scores from the first test. If I'm looking at the scores from the first test, anybody who scores in maybe the upper quartile, I'm not going to be concerned about their grades. People who are in the middle 2 quartiles, quartile 2 and 3, maybe I'm a little less concerned, but I'm going to keep an eye on them. It's the ones who fall down into this bottom quartile that maybe I'm going to have a chat with about how to prepare for later exams. Let's pull that. So when we get to say larger groups, say regional groups, students, if we look at SAT scores for students who are trying to apply to Springfield College versus Winnick versus UMass, you have a regional group. It's maybe we don't want to break down small percentiles because each percentile is only going to have maybe 5 students. We don't want to break into quartiles because the numbers will be too big. There'll be a couple hundred students per quartile. Then maybe we could use deciles, where deciles cover 10%. Now, the last major point that I want to make across here is notice the equivalency. Decile 9 is the same thing as percentile 20. Quartile 3, which is the same thing as percentile 75. And I think my favorite one here is the median, which we learned in measures of central tendency, is that middle score is the same thing as quartile 2, the same thing as decile 5, and the same thing as percentile 50. Now, the second type of measures of position are standardized scores. These are other ways of representing data in a standardized format where we take away the units, or for that matter, we take away the means and standard deviations. what we have done here is we standardize data for multiple data sets so that they have the same mean and the same standard deviation. Now, the most common format that you're going to learn is a z-score, where a z-score has a mean of 0 and a standard deviation of 1. There are other standardized scores. This is the one that we're going to cover in this class. This represents the number of, where the standard deviation represents the score, or one standard deviation from the mean. Now, the calculation for a z-score looks pretty similar to variance, or standard deviation, if you see. Now, here we see it, it's z equals x minus the mean over standard deviation. And what this allows us to do is, if we go back to our two different classes, we have, let's say, two students who scored a 77 in both of those classes. Now, a z-score, like we said, has a mean of 0 and a standard deviation of 1. So if I plot these scores, 2, 3, now I want to put the person in data set A. I calculate their z-score. I take 77 minus the score, or a mean of 80, and then divide by 10. What I have here is a z-score of negative 0.333. So they're going to fall somewhere around here, z of negative 0.333. The other student got a 77 as well. So their x values are the exact same, but we can see their actual class tests were not the same at all. The mean on this test was a 90, where the mean on this test was an 80. So this test was much harder. The standard deviation of the variability was very small for this test, where the variability for this test was much larger. So when this person gets a 77, their z-score is actually a 2.67, or 2.6, so they're down here, z equals negative 2.6. So getting the exact same raw data point actually is not equivalent to the same score. The person in data set A did much better on the normal distribution than the person in data set B. And that's a pretty important concept. Now, generally when you calculate scores, z-scores are different because they are based on different means and different standard deviations. So Class A and Class B had different means and standard deviations. You can see that the person in Class A performed better in this example. Now, generally what you'll see is if the z-score, or if your x-score is above the mean, then you'll have a positive z-score. As we said, since the mean equals 0, if your x-score also equals the mean, you'll have a z-score of 0. And if your x-score is below the mean, you'll have a negative z-score. These are pretty important concepts. Make sure that you review them. I have an example video posted, or linked to. It's not embedded in, just because it's not required watching, but it'll help you review this concept and apply it.